Let's start with a word everyone uses but almost nobody defines carefully: reliable. Everybody has an intuitive sense of what it means. But intuition isn't enough when you're designing a system. So let's be precise. For software, reliability means 4 specific things. 1. The application performs the function that the user expected. Not a close approximation, the actual thing they asked for. 2. It can tolerate the user making mistakes, or using the software in unexpected ways. Users will always surprise you. A reliable system doesn't fall apart when they do. 3. Its performance is good enough for the required use case, under the expected load and data volume. Being correct doesn't count if it takes 10 seconds to respond. 4. It prevents unauthorized access and abuse. Security is part of reliability. If those 4 things together mean working correctly, then we can define reliability as meaning continuing to work correctly even when things go wrong. The things that can go wrong are called faults. A system that anticipates faults and can cope with them is called fault-tolerant or resilient. Now here's a distinction the book makes that most people miss, and it matters a lot in practice. A fault is not the same as a failure. A fault is when one component of the system deviates from its specification. A failure is when the system as a whole stops providing the required service to the user. The goal is never to eliminate all faults, that is simply not possible. Every complex system will have faults. The goal is to build fault tolerance mechanisms that prevent individual faults from cascading into full system failures. It is generally better to design these mechanisms and test them deliberately than to hope faults never happen. And this brings us to one of the most counterintuitive ideas in the book. In some fault-tolerant systems, it can actually make sense to deliberately increase the rate of faults by triggering them on purpose. Netflix built a tool called Chaos Monkey specifically to do this. It randomly kills individual processes in their production systems without warning, during business hours. Why would you deliberately break your own production system? Because many bugs are actually due to poor error handling. By forcing faults to happen constantly and randomly, you ensure that your fault tolerance machinery is continuously exercised. You build genuine confidence that when a real fault hits at 3 a.m. on a Friday night, the system knows exactly what to do. Testing fault tolerance only in staging environments gives you false confidence. There is one exception: some faults are better prevented than tolerated. Security breaches are the clearest example. If an attacker has compromised your system and accessed sensitive data, that event cannot be undone. For security faults, prevention is the goal. For most other faults, hardware failures, software bugs, human errors, the goal is tolerance. The most obvious kind of fault, and the one engineers think about first, is hardware failing. Hard disks crash. RAM becomes faulty. Power grids have blackouts. Someone in the data center unplugs the wrong network cable. This happens more often than you'd think. Anyone who has worked with large data centers will tell you, these things happen all the time when you have a lot of machines. Let's make this visceral with real numbers. Hard disks are reported to have a mean time to failure, that's the average time before a disk dies, of somewhere between 10 and 50 years. 10 to 50 years. That sounds safe. You'd never expect a disk to die in your lifetime. But now let's do the math at scale. A storage cluster with 10,000 disks, not large by modern standards, many companies have far more, should expect roughly one disk to die every single day. Not once a year. Not once a month. Every single day. At that scale, hardware failure is not an exceptional event. It is a daily operational reality. So what's the standard response? Redundancy. Add redundant hardware components so that when one fails, its backup can take over. Disks are set up in RAID configurations so a single disk failure doesn't lose data. Servers have dual power supplies so one power unit failing doesn't take the server down. Data centers have batteries and diesel generators so a power grid failure doesn't kill the facility. When one component dies, the redundant component takes its place while the broken one is replaced. This approach has worked extremely well and has been the backbone of reliable computing for decades. However, something has shifted in recent years. As data volumes have grown dramatically, and as applications now routinely run across hundreds or thousands of machines, a new challenge has emerged. AWS, for example, is explicitly designed to prioritize flexibility and elasticity over single machine reliability. It's actually fairly common for virtual machine instances to become unavailable without warning. In this environment, hardware redundancy alone isn't enough. The trend is toward software fault tolerance, designing the software itself to survive the complete loss of entire machines, not just individual components. This creates a significant operational benefit beyond just disaster recovery. A system designed to tolerate losing a machine can also enable rolling upgrades. Instead of taking the entire system down for maintenance, you take one node out of rotation, patch it, and bring it back. Then repeat for the next node. Zero downtime. No scheduled maintenance windows at 2 a.m. Hardware faults are random and independent. When one machine's disk fails, it has absolutely no effect on whether any other machine's disk will fail. There may be weak correlations, machines in the same server rack might share a power supply, for example, but broadly speaking, hardware faults are uncorrelated. That independence is what makes hardware redundancy work. You're simply playing the law of large numbers. Software errors are a completely different category of fault, and they are far more dangerous. They are systematic and correlated. One bug in your software can cause every single instance of your application across every machine in your entire infrastructure to fail simultaneously. Consider what happened on June 30, 2012. The atomic clocks used for internet time synchronization added a leap second, a 1-second correction to keep atomic time aligned with astronomical time. A bug in the Linux kernel's handling of this event caused a massive number of servers across the internet to hang, all at exactly the same moment. Not one company, not one server, thousands of servers from dozens of companies, all running the same kernel version, all failing together. That's the terrifying characteristic of software faults. They are correlated across all instances that share the same code. The book gives more examples of this category. A runaway process that consumes all available CPU, memory, disk space, or network bandwidth, starving every other process sharing that resource. A service that becomes slow and unresponsive, triggering cascading failures as other services that depend on it start queuing up and eventually timing out or crashing too. A service that starts returning corrupted responses, silently poisoning the data processed by downstream systems. What makes these especially treacherous is how they behave over time. These bugs often lie completely dormant for months or even years. The software makes some assumption about its environment, about input formats, about timing, about ordering of events, and that assumption is usually true. Until one day, under an unusual combination of circumstances, it stops being true. And then everything breaks at once. There is no silver bullet for systematic software errors. What helps is a combination of practices: carefully thinking through the assumptions your system makes and making them explicit, thorough testing at all levels, process isolation so one misbehaving process can't bring down others, designing processes to crash quickly and restart cleanly rather than limping along in a corrupted state, and most critically, measuring and monitoring actual system behavior in production. One specific pattern the book mentions: if a system is supposed to maintain an invariant, for example, that the number of messages entering a queue always equals the number of messages that eventually leave it, build the system to check that invariant continuously and raise an alert the moment it's violated. Don't wait for users to report problems. Detect them first. Here's the most uncomfortable finding in this entire chapter. Humans design the software. Humans build it. Humans operate it. And humans are the single largest source of production outages, not hardware, not software bugs. One large-scale study of internet services found that configuration errors by operators were the leading cause of outages. Hardware faults, the thing we spend so much time building redundancy for, played a role in only 10 to 25% of outages. The leading cause was people making mistakes when configuring systems. Humans are known to be unreliable in this specific way, even when they are highly skilled and well-intentioned. So how do we build systems that remain reliable despite being operated by fallible humans? The book identifies several complementary strategies that work together. First, make the right thing easy and the wrong thing hard. Design systems, APIs, and admin interfaces so that doing the correct thing is the obvious, natural path. If your configuration format makes it trivially easy to accidentally point a production service at a development database, that's a design failure. Fix the design. However, this balance is tricky. If the interface is too restrictive, operators will work around it, which usually creates bigger problems. Second, decouple the places where people make mistakes from the places where those mistakes cause damage. Provide a fully featured sandbox environment, ideally with realistic data, but isolated from production, where operators can explore, experiment, run tests, and yes, make mistakes safely. Let people get comfortable with the system without risking real users. Third, test thoroughly at every level. Unit tests. Integration tests. Manual tests of rare scenarios. Automated testing is particularly valuable for covering the corner cases that almost never come up during normal operation, but those are exactly the cases where human error is most likely to cause a mistake that goes undetected. Fourth, allow quick and easy recovery. When someone makes a mistake, and the cost of that mistake is directly proportional to how long it takes to undo. Fast rollback of configuration changes. Gradual code rollouts that only expose new behavior to a small percentage of users at first. Tools that let you recompute data if you discover the old computation had a bug. The faster you can reverse a bad change, the less damage any given mistake can cause. Fifth, and this is the one most teams underinvest in, set up detailed monitoring. In other engineering disciplines, this is called telemetry. Once a rocket has left the launch pad, you cannot go up and physically check what's happening. You rely entirely on instruments that report data back to you. Production software systems are the same. Detailed metrics, error rates, performance dashboards, and alerting systems give you visibility into what's actually happening, including early warning signs before a problem becomes a full outage. Monitoring lets you check whether the assumptions your system is making are actually holding in production. When they stop holding, you want to know before your users do. You might think reliability is only a critical concern for systems where lives are literally at stake: nuclear power plants, air traffic control systems, medical devices. Those systems absolutely need to be reliable, and they invest heavily in it. But reliability matters everywhere there's data that real people care about. Consider the book's example. Think about a parent who stores all of their family's photos and videos in your application. Every birthday photo. Every video of a child's first steps. Every holiday memory, all of it, trusted to your system. How would that parent feel if your database was suddenly corrupted and all of those memories were gone? Would they even know how to restore from a backup? Do you have a backup they can actually use? This isn't hypothetical. Services lose user data. It happens. And the human cost is real even when no one is physically harmed. Beyond the personal, consider the business. Bugs in business applications cause lost productivity and legal risk. If financial figures are reported incorrectly due to a software bug, there are regulatory consequences. Outages of e-commerce sites have enormous measurable costs. Amazon has published data showing that a 100 millisecond increase in response time reduces their sales by 1%. A 1-second slowdown reduces a key customer satisfaction metric by 16%. Those are not estimates, they are measured. Every millisecond of unreliability is costing money. Now, and the book is balanced about this, there are situations where it makes sense to deliberately sacrifice some reliability. When you're building a prototype for an unproven market and need to validate whether anyone will pay for your product at all, investing heavily in fault tolerance before you know if the product has a future is premature. When operating a service with very thin margins, you might rationally accept a slightly higher error rate to control costs. These are legitimate engineering and business trade-offs. The book doesn't say reliability must always be maximized. What it does say is this: be conscious of it. Make the decision explicitly. Know exactly which corners you are cutting, why you are cutting them, and what the consequences might be. What you never want is to discover after the fact, after the data is gone, after the extended outage, after the legal action, that you were cutting corners without ever having made a deliberate decision to do so.